Hello everyone, and welcome to today's lecture on the Convergence outlook for 2026. If we look back at the history of technological progress, we often analyze it through a linear, reductionist lens. We study the steam engine, the assembly line, the internet, or mobile computing as distinct, sequential waves. This is Joseph Schumpeter's classic framework of creative destruction, where one paradigm is gradually dismantled to make way for the next. But as we enter 2026, we are witnessing a fundamental disruption in the timing and mechanics of this creative destruction. Look closely at the diagram on the right side of your screen. This is not a clean, linear progression. It is a highly tangled, multi-vector knot. The core thesis of our lecture today is simple yet profound. The future no longer arrives one trend at a time. Instead, we are entering an era of compounding, overlapping, and systemic collisions. Over the next hour, we will deconstruct how these collisions are reshaping our physical, biological, and digital architectures, and what this means for strategic leadership. Let us begin with a methodological critique. As advanced students of strategy, you must understand why we have officially retired the traditional corporate trend report. For decades, consulting firms and research agencies have published annual reports listing the top 10 trends to watch. This is what we call the old way. It is inherently flawed for three reasons. First, it isolates domains. It looks at artificial intelligence in one silo, synthetic biology in another, and energy systems in a third. Second, it assumes parallel, independent tracks of technological advancement. And third, its primary utility is passive. It merely helps you see what is coming. In the convergence era, we must reject this reductionist view. As shown in our table, we now focus on compounding system collisions. We must operate under the assumption that changes do not just move forward linearly. They spread sideways across industries, often faster than they move forward. Our goal is no longer passive foresight, it is active, strategic decision-making in real time. Look at the visual metaphor below the table. We have crossed out the linear timeline. It is dead. In its place, we have a dynamic system of nodes, feedback loops, and multi-directional vectors. When these nodes collide, they don't just add up, they multiply. Let's look at the underlying rules governing this new reality. To navigate this landscape, we have established the 4 rules of convergence. These act as our structural pillars, much like the classical columns you see illustrated on the right. Rule number 1, system-level changes. We are no longer dealing with simple product substitutions. These changes operate across entirely different domains and pile on top of each other. Think of how advancements in battery chemistry collide with decentralized computing, which in turn alters logistics networks. Rule number 2, net new realities. When multiple exponential technologies mature simultaneously, they create a phase transition. What seemed completely inconceivable 5 years ago suddenly becomes economically and technologically inevitable today. Rule number 3, the redistribution of power and value. Convergence rewrites the competitive dynamics of entire industries. Value does not remain static. It migrates. Traditional barriers to entry collapse, and the point of control shifts from end product manufacturers to upstream infrastructure providers. And rule number 4, these shifts are exceptionally hard to reverse. Once multiple systems lock into place and reinforce one another, they establish a new, highly stable market equilibrium. Economists call this systemic hysteresis or path dependency. Keep these 4 rules in mind as we analyze the macroeconomic and geopolitical landscape of 2026. Before we look at specific technology stacks, we must map the terrain. The global operating environment of 2026 is best represented not by a flat grid, but by this highly complex topographic elevation map. Every decision you make as a strategic leader will be influenced by these shifting elevations. Let's break down the 4 critical dimensions of this terrain. First, technology. We are undergoing a massive paradigm shift. We are transitioning from discrete, isolated tools like a software application you open and close to tightly coupled, autonomous cyber-physical systems. These systems are defined by their ability to sense the environment, decide on a course of action, and act physically without human intervention. Second, the economic landscape. We see an extreme concentration of top-heavy power. Growth is no longer dictated simply by market demand, but by severe bottlenecks in the physical layer. specifically raw compute capacity, access to foundational AI models, and end-user distribution networks. Third, the geopolitical dimension. We are seeing a return to infrastructure-led power dynamics. Semiconductor fabrication facilities, grid-scale energy generation, and critical mineral supply chains are no longer viewed merely as commercial assets. They are treated as the very foundations of national security and sovereign survival. And finally, demographic pressures. The rapidly aging populations in key economic engines such as the United States, China, and Japan are forcing a hollowing out of the traditional workforce. This demographic deficit is the primary macroeconomic accelerator for automated, autonomous, and robotic care systems. Do you see the convergence here? Demographics drive the demand for automation. Geopolitics controls the chips that power it. Economics defines who can afford it. And technology delivers the execution. They are completely inseparable. Let us dive into our first major paradigm shift. Power is physical again. For the past 3 decades, the tech industry operated under the illusion of weightlessness. We talked about the cloud as if it were an ethereal, atmospheric construct. In 2026, that illusion has shattered. Artificial intelligence has forced a brutal return to physical, thermodynamic, and geographic infrastructure constraints. Let's look at the first critical implication: compute shock and water intensity. As neural networks grow exponentially, the power density of server racks is skyrocketing. Traditional air cooling is no longer physically viable. Data centers are rapidly converting to liquid and direct-to-chip immersion cooling. As a direct consequence, local hydrology has become a primary gating factor for digital expansion. You cannot scale digital intelligence without massive, uninterrupted access to freshwater. The second implication is the structural tension between centralization and the edge. This is a classic architectural trade-off. Training state-of-the-art models requires massive, centralized facilities with direct access to nuclear-scale power grids. However, latency-sensitive inference actually running the AI models in real time on autonomous vehicles or factory floors pulls compute power back to the physical edge. Look at the illustration on the left. It perfectly captures this new reality. The digital microchip is now physically and conceptually welded to the industrial cooling tower. The software layer is entirely bound by the laws of thermodynamics. To understand how we will solve these thermodynamic bottlenecks, we must analyze the polycompute matrix. We are no longer living in a mono-computing world dominated solely by silicon-based CPUs. We now rely on 3 distinct, coexisting computational paradigms. On the left, we have classical computing, which in 2026 is heavily optimized for neural processing units and GPUs. This architecture is exceptionally fast at processing structured data, but it is not inherently exponential in its efficiency. We use it for daily automation, code generation, and semantic search. It is highly capable but incredibly power-hungry. In the middle, we have quantum computing. This is a fundamentally different mathematical paradigm. By utilizing cryogenic qubits, quantum processors exploit superposition and entanglement to achieve exponential speedups for highly specific, complex problems. We do not use quantum computing to write emails. We use it to simulate quantum chemistry, discover new materials, and crack advanced cryptographic systems. And on the right, we have perhaps the most radical shift: biocomputing. This represents the ultimate convergence of biology and computer science. By using synthetic biology to interface living human brain cells with silicon chips, researchers are building wetware processors. These biological computing units are orders of magnitude more energy efficient at the edge than silicon, and they provide intrinsic neuromorphic security. As a strategic leader, your role is not to choose one of these technologies. Your role is to orchestrate how these 3 distinct computing paradigms interface with one another to solve complex operational challenges. Our second core shift is the transition of artificial intelligence from a passive advisor to an active agent when machines take the wheel. Let us trace the evolutionary pipeline of this technology. We began with Step 1, copilots. This is what most people became familiar with between 2022 and 2024. These are stateless systems. They wait for a human to write a prompt, and they generate text or code in response. The human is entirely in the loop, acting as the decision maker and the executor. We are currently in Step 2, persistent agents. These are systems, like the open-source OpenClaw framework, that do not require constant human prompting. They maintain long-term context, manage their own state, and can execute shell commands locally on an operating system to achieve a broad goal. We are rapidly moving toward Step 3, multi-step execution. These are fully sovereign agentic networks. They automate complex, end-to-end business workflows across communication channels, local file systems, and external APIs entirely without human supervision. But I want to draw your attention to the absolute bottleneck of this transition, noted at the bottom of the slide. Reliability and containment, not raw capability, are the primary gating factors for agentic deployment. It is easy to build an agent that works 70% of the time, but in enterprise environments, a 30% failure rate is catastrophic. The challenge for 2026 is building the testing sandboxes and guardrails to ensure these agents do not hallucinate, mutate, or cause systemic operational failures. This agentic capability brings us to the new labor equation. How do we structure organizations and operations when human labor is no longer the sole unit of productivity? To answer this, we must look at the 5-layer stack illustrated on the left side of the slide. At the very foundation, we have Layer 1, physical infrastructure. This is the domain of robotics, additive manufacturing, and physical component production. Without physical actuators, digital intelligence cannot alter the real world. Directly above that sits Layer 2, digital infrastructure. This is the real-time inference layer, consisting of localized edge compute nodes and hyperscale data centers that process sensory data. On top of digital infrastructure is Layer 3, compute infrastructure. This layer governs data storage, vector databases, and memory retrieval mechanisms, ensuring our autonomous systems have stable, real-time access to operational history. Then, we have Layer 4, operational systems. These are the orchestration frameworks, the middleware, and the multi-agent automation software that translate high-level business goals into specific machine tasks. And at the very top, we have Layer 5, resilience and security. This is the defensive shield. It is the layer that protects the entire stack from systemic disruptions, cybersecurity threats, and model poisoning. Look at the robotic assembly line on the right. This is not just automation of manual labor. It is the physical manifestation of this entire 5-layer stack working in perfect harmony. Human labor in 2026 is rapidly migrating from executing tasks within the stack to supervising, auditing, and securing the stack itself. Our third core shift is deeply personal and ethically complex. We are transitioning into a world that watches back. For years, we viewed computing as a one-way street. We looked at a screen, and we input data. In 2026, the environment has become bidirectional. The digital world is continuously monitoring, analyzing, and adapting to our physical and biological states. Let's examine 3 vectors of this shift. First, always-on biometrics. We have moved far beyond simple step counting. Consumer wearables and ambient sensors now track continuous sleep architectures, physiological stress responses, and real-time glucose levels. This continuous monitoring turns human health into an active, real-time feedback loop. Second, smart implants. We are seeing the rise of inside-the-body systems. These micro-devices detect subtle biological changes such as early inflammatory markers or neurotransmitter drops and trigger automated, targeted drug dosing and medical interventions directly inside the patient. And third, brain-computer interfaces, or BCIs. Neural interfaces are rapidly transitioning from academic laboratory demonstrations to practical clinical applications. As signal-to-noise ratios improve, patients with motor impairments are achieving precise control over external software and robotic prosthetics. Look at the graphic. It is a technical schematic of an eye, but the lens is a camera aperture. It symbolizes a profound truth. In 2026, the boundary between biological perception and machine surveillance has completely dissolved. The logical culmination of a world that watches back is the creation of digital twins of the self and the rise of what sociologists call the corporate panopticon. Let us dissect these 2 concepts. A digital twin of the self is not a static profile. It is a highly dynamic, real-time simulation of an individual's unique physiology, behavioral patterns, and cognitive tendencies. By feeding continuous biometric data streams into these models, platforms can simulate how you will react to stress, fatigue, or specific visual stimuli. This allows organizations to design highly individualized performance, health, and productivity interventions. But this capabilities landscape is fraught with severe governance failures. Major platform ecosystems are intentionally bundling hardware devices, operating systems, and proprietary healthcare software to create absolute consumer and enterprise lock-in. As a result, we are seeing intense legal and ethical battles over neural signal privacy, behavioral data portability, and employer ownership of cognitive data. Look at the illustration on the right. The physical person stands upright, but their shadow is cast as a highly structured, digitized grid. That digital shadow is what corporations are modeling, pricing, and controlling. The strategic question for the next decade is, who owns your digital twin? Is it you, or is it the corporation that manufactured the sensor on your wrist? Our fourth core shift takes us to the frontier of cyber-physical integration, when systems become alive. This is not a metaphor. In 2026, we are seeing machines display behaviors that were previously reserved exclusively for biological organisms, specifically continuous adaptation, real-time learning, and organic integration with their environments. We see this across three domains. First, continuous AI. Traditional machine learning models were static. They were trained, deployed, and remained frozen until the next update. Today, we are deploying always-on, continuous learning models. They transition from merely recommending a course of action to autonomously executing, routing, scheduling, and triaging workflows in real time. Second, ambient sensing. Dense, high-fidelity sensor networks embedded in smartphones, factory floors, and autonomous delivery vehicles have turned the physical world into a continuous, real-time perception feed for machine intelligence. And third, embodied adaptation. Artificial intelligence is breaking free from the digital screen and integrating directly with physical space. We see this in real-time enterprise deployments. Amazon is testing the bipedal robot Digit to revolutionize warehouse logistics. BMW is trialing Figure AI's humanoid platforms on its assembly lines. And DHL is rapidly deploying Boston Dynamics Stretch Robot to automate trailer unloading. Look at our visual on the right. The cold, steel robotic arm is being animated and wrapped by living, growing flora. This represents the synthesis of mechanical engineering and organic adaptability. Our machines are no longer static tools. They are dynamic, adaptive systems that grow alongside the environments they inhabit. If machines are becoming more organic, then biology is simultaneously becoming more programmable. Welcome to the era of programmable biology and the platform model. For over a century, biotechnology was characterized by empirical discovery, essentially trial and error in wet labs. In 2026, we operate under a completely different thesis. DNA and living cells have become a programmable substrate. We can now treat genetic sequences as reusable, modular software components, complete with version control and standardized APIs. This shift is driven by the circular engine you see on the left, the design, build, test, learn flywheel. We begin with design. Advanced computational models and generative AI analyze millions of protein structures to suggest highly optimized molecular candidates for a specific task. Next is build. Automated robotic biofoundries synthesize these physical materials and genetic constructs with high precision. Then we test. Closed-loop, high-throughput screening systems validate the real-world performance of these synthetic organisms. And finally, we learn. The experimental data is fed directly back into our machine learning models, creating a compounding flywheel of computational accuracy. Look at the graphic on the right, the DNA helix constructed of gears. This is the visual definition of bioconvergence. We are applying the rigorous, predictable engineering principles of software development to the complex, self-replicating medium of biological life. Let us examine the biological platform in action with three extraordinary real-world breakthroughs that have matured in 2026. First, smart biomaterials. Researchers at Sweden's Keith Royal Institute of Technology have engineered transparent wood. This material not only transmits light, making it highly valuable for energy-efficient architecture, but it can also bend and absorb impacts without shattering. Second, living infrastructure. Engineers at MIT have mixed standard cement with carbon black, a highly conductive carbon material. This turns concrete into a massive grid-scale supercapacitor. By utilizing this technology, we can store renewable energy directly within the structural foundations of our houses and the very roads we drive on. And third, programmable cells. We are now engineering microorganisms to act as localized chemical factories. These cells are designed to sense specific environmental inputs, process that information internally, and produce targeted outputs such as pharmaceuticals, biofibers, or catalysts completely on command. We have covered a massive amount of conceptual terrain today. Let us now synthesize these insights by looking at the convergence landscape as a unified system. I want you to study this engineering blueprint carefully. This is the machine of modern industrial reality. On the left and top, we see the external engines of change: global energy constraints, demographic labor shortages, exponential advancements in artificial intelligence, and shifting geopolitical trade alliances. These are not isolated pressures. When they enter our industrial machine, they collide and generate the core convergences we have dissected today: the thermodynamic realities of compute shock, the autonomous execution of agentic economies, the computational predictability of programmable biology, and the cyber-physical integration of living intelligence. The ultimate result of this system is depicted on the right: the complete collapse of the traditional boundaries between science, manufacturing, and software. In the 20th century, a software engineer did not need to understand molecular biology, and a materials scientist did not need to understand neural network architectures. In 2026, that siloed specialization is a recipe for strategic obsolescence. To lead in this environment, you must be a systems architect. You must understand how digital code animates physical infrastructure and how biological systems can be leveraged to solve digital bottlenecks. We conclude today's lecture with the most critical question of all: what must you, as leaders, do next? To navigate this terrain, you cannot rely on old strategic playbooks. You need a new navigational compass, much like the one illustrated on the right, placed directly over our blueprints for future construction. We have structured these actions into 3 strategic pillars. Pillar 1, Scenario Plan Now. If you are waiting for market confirmation before you adapt your business model, you are already too late. In a world of compounding exponential changes, wait and see is a strategy of slow death. You must actively stress test your operational assumptions against radical, non-linear disruptions today. Pillar 2, Engage regulators early. Do not treat regulatory compliance as an afterthought. You must proactively help shape evidence standards, safety guardrails, and liability frameworks while they are still in their draft stages. Safety, ethical alignment, and accessibility cannot be retrofitted onto an existing cyber-physical system. And Pillar 3, Prepare for geopolitical spillovers. You must meticulously map your supply chain dependencies, track semiconductor adoption timelines, evaluate power grid vulnerabilities, and assume that the foundational technologies your business relies upon will become battlegrounds for strategic global competition. The future is not something that happens to us. It is an architecture we build. By understanding the rules, the shifts, and the mechanics of convergence, you have the opportunity to design that architecture. Thank you for your attention today.